Welcome to all of you in my YouTube channel Physics Cafe by Manjeet Kaur. In this video, we study about D'Alembert's principle. In D'Alembert's principle, we have number of particles in a system. This is our diagram of D'Alembert's principle. And in this, we take two type of cases. In case 1, when the system is in equilibrium, then the force acting on the ith particle will be 0. That means the particle is at rest, it doesn't move from its mean position. So it doesn't cover any distance, so force on that particle will be 0. And in case 2, when the system is dynamic, then the particle cover some distance. That means it moves from its original position and comes at here. So that distance which it covers is called its virtual displacement. That means in dynamic system, when the particle is moving on the surface and the force of constraint will be perpendicular to the displacement. And in this we have two type of forces. First force is applied force and second force is constraint force. So that in this, when the particle moves some distance, which is virtual displacement and is denoted by delta Ri. So first write its definition. For a system of masses of particles, the sum of the differences of the forces force acting on the system and the time derivative of the momenta is 0 when projected it only any virtual displacement. That means for a system in which we have number of particles, when we apply forces, that means constraint force or applied force, the difference of the forces acting on the system and the time derivative of momenta is projected and we get the virtual displacement. That means हमारे पास नंबर ऑफ पार्टिकल्स है जिसमें हम फोर्स अप्लाई कर रहे हैं, कौन कौन सा, अप्लाइड फोर्स एंड कंस्ट्रेंट फोर्स, उन दोनों का डिफरेंस एंड मोमेंटा का डेरिवेटिव. तो हमें किसके क्या क्या वैल्यू मिलती है, वर्चुअल डिस्प्लेसमेंट की. आई होप कि आपको डेफिनेशन क्लियर होगी कि वी हैव नंबर ऑफ पार्टिकल्स इन अ सिस्टम एंड वी अप्लाई द डिफरेंसेस ऑफ फोर्सेस विच आर कंस्ट्रेंट फोर्स एंड अप्लाइड फोर्स एंड द derivative of momenta which is mass into velocity, then we get virtual displacement which is delta Ri. Now start its derivation. Derivation of D'Alembert's principle. Consider there are two possible configuration system of particles at any instant of time t, which are constant with the forces which are applied force and constraint force and constraint imposed on the system. That means this is our system and we take two possible configurations. We take two possible configuration at any time t when we apply force, which are constraint force and applied force. Now when we apply force, that means that my particle moves from here to here. So right here, if the system of the particle moves, if the system of the particle goes from one configuration to the another, then each particle of the system is imagined to be displaced by an infinitesimal vector, which is delta Ri, is known as virtual displacement. That means if the system of particle goes from one configuration to the another, that means when the particle moves from here to here, then we imagine as that each particle goes from its mean position to here, then it covers some distance which is known as virtual displacement, which is delta Ri. That means हमारे पास कोई सिस्टम है जिसमें नंबर्स ऑफ पार्टिकल्स हैं, देन अगर वो थोड़ा सा भी डिस्टेंस मूव करते हैं तो हमें क्या मिलता है, वो डेल्टा आर आई, विच इज़ वर्चुअल डिस्प्लेसमेंट. देन जब वो उसने अपना कुछ डिस्टेंस, ओरिजिनल डिस्टेंस कवर अप कर लिया, मतलब वो ओरिजिनल उसकी प्लेस थी वहाँ से वो मूव होके कोई और प्लेस पे आ गया है, देन we get delta Ri, which is virtual displacement. Now we take its cases. We have case number 1 when the system is in equilibrium. Case 1 when the system is in equilibrium. When the system is equilibrium, then the force acting on the ith particle will be 0. So right here, in this, the force acting on the ith particle will be 0. That means the particle stays at rest, it doesn't cover any distance. So when the force acting on the ith particle will be 0, so we can write Fi, which is equals to 0, and we know delta W, which is virtual work. Virtual work means small work, which is equals to Fi dot delta Ri, which is virtual displacement, and this is our force, which is equals to 0 because particle stays at rest, it doesn't cover any distance. This is equation number 1. Now Fi, which is our force, which is the sum of applied force and constraint force. Now put the value of Fi in equation number 1. So we can write, put the value of Fi in equation number 1. So we can write it here. Here we taken summation I Fi A plus F dot delta Ri, which is equals to 0. Now we open bracket and multiply delta Ri inside this. So from here we can write summation I Fia plus F dot delta Ri, which is equals to 0. So we multiply delta Ri inside this. So we can write summation I Fia, which is applied force, into virtual displacement plus constraint force into virtual displacement equals to 0. Now next we get delta W, which is our small work, is equals to Fia, which is applied force, plus constraint force delta Ri. So we get delta W, which is equals to summation I Fia dot delta Ri. That means in equilibrium our constraint force will be 0. So we get delta W is equals to summation I constraint force into applied force into virtual displacement. And in this value we write here, in equilibrium due to applied force constraint force is 0. So this value become 0. So we get delta W, which is equals to Fia into delta Ri. That means in virtual work we get the value of applied force with displacement. Now we take second case when the system in dynamic. In this, when we take this case, that means the system has number of particle and the number of particle moves some distance. Then we get the value of virtual work with constraint force. So we can write, suppose the particle is moving on the surface of the sphere and the constraint force will be perpendicular to the displacement. That means here our constraint force is not equals to 0. That is perpendicular to the displacement. In that case, in which the particle moves some distance, and we get the value of delta Ri. So we can write Fi dot delta Ri. This is our constraint force is equals to F dot delta Ri cos 90 degree. Why cos 90 degree? Because constraint force is perpendicular to its displacement. So we know cos 90 degree is equals to 0. So put the value of cos 90 here. We get F dot delta Ri 0, which is equals to 0. So constraint force into virtual displacement equals to 0. So we write this equation in summation form. So we get summation F dot delta Ri is equals to summation applied force dot delta Ri is equals to 0. So this is known as principle of virtual work. So we get delta W is equals to summation Fia dot delta Ri, because the constraint force is perpendicular to displacement. So we get small work is equals to summation applied force into virtual displacement. This is our virtual work. Now, according to Newton's second law of motion, according to Newton's second law of motion, which is force, which is change of momentum with respect to time, we can write F is equals to dp upon dt. So we can write in classical mechanics Fi, which is equals to pi dot, because we write derivative like this. So we can write this equation equals to 0. So right here Fi minus pi dot is equals to 0. Now we take virtual displacement. So Fi minus pi dot into virtual displacement is also equals to 0. Now we have to put here the value of force, which is constraint force and applied force. Now put the value of Fi summation I applied force plus constraint force minus pi dot delta Ri is equals to 0. In this, we take when the system is in dynamic, then this is our force, their sum and difference of momentum. So multiply delta Ri with this. So open it, summation I Fia minus Pi dot delta Ri plus Fi dot delta Ri equals to 0. This is our difference of applied force and momentum, that which is change in momentum, and this is our constraint force. So we can write summation I Fia minus Pi dot delta Ri plus summation I Fi dot delta Ri is equals to 0. Again, virtual work by the force of constraint will be 0. So therefore, we can write from here summation I Fia, which is applied force and change in momentum, plus summation I constraint force will become 0. Again, virtual work by force of constraint will be 0. Therefore summation I Fi dot delta Ri is equals to 0. That means we take constraint force, again become 0. So this equation will become 0. So we get the value of D'Alembert's principle. So this value becomes 0. So we can get from here summation I Fia, which is applied force and change in momentum with respect to time dot delta Ri equals to 0. So this is the equation of D'Alembert's principle. So this equation is known as D'Alembert's principle. So I hope कि आपको clear होगा. Again I discuss all once. This is our diagram in which we have number of forces, number of particles. So we have two type of forces. First is applied force and second is constraint force. And we have two type of cases. First is equilibrium and second is dynamic. When the system is in equilibrium, then the force acting on that particle will become 0. So constraint force will become 0. And in case second, when the particle moves some distance, then we get the difference of forces and change in momentum. Then we get the value of delta Ri, which is virtual displacement. So this is the above definition in which we already explained. For a system of mass of particle, that means we have number of particle, then the sum of differences of the force acting on this system, which is applied force and constraint force, and the differences means change in momentum with respect to time, this value. So Then we get the virtual displacement. Now we write its derivation. In this I explain the particle is covers some distance, that means it from this configuration it moves at it moves some distance at any time t, then we get the value of delta Ri. So in case 1 I explain the force acting on the ith particle will be 0. So Fi equals to 0. So virtual work which is Fi dot delta Ri. Fi is our force which is the sum of applied force and constraint force. So I put the value of Fi here. So we get summation I Fia plus F dot delta Ri is equals to 0. Then virtual work will become Fia plus F dot delta Ri. Now, because the system is in equilibrium, so constraint force will become 0. So we get delta W is equals to Fia dot delta Ri. Now in second case, when the system is in equilibrium, that means suppose a particle is moving on the surface of the sphere, the constraint force will become 0, will become perpendicular to the displacement, then F dot delta Ri is equals to F dot delta Ri cos 90 degree. Cos 90 degree we know which is equals to 0. So F dot delta Ri, put the value of 90 degree, so we get 0. Okay, so F dot delta Ri will become summation Fi A dot delta Ri is equals to 0. This is known as virtual work. So then we apply Newton's second law of motion. Newton's second law of motion, which is change in momentum. So we can write change in momentum like this, Fpi dot. So we take the difference, that means equals to 0. Fi minus pi dot is equals to 0. Now multiply with delta Ri. So put the value of F here, which is applied force and constraint force. Then separate Fia minus pi dot, that means applied force and change in momentum and constraint force. Then we again virtual work of the constraint force will become 0. So this equation again become 0. So we get the value of again virtual work by the force of constraint will be 0. Therefore we get the value of summation I Fia minus pi dot delta Ri is equals to 0. So this equation is known as D'Alembert's principle. So I hope I clear your all doubts. So guys, like my video, subscribe my channel. Thank you.